today I'm going to discuss measuring displacement as a function of time. Now for that you need sensors connected to SEELab. In this case I'm using the SR04 echo module where supply is connected to the 5-volt signal there. You have the trigger pin which comes from SQ2. The echo signal is connected to IN2 which measures precise time intervals, and ground is common, connected to just ground. Now the objective here is to measure the displacement of the spring as a function of time in order to find out the frequency of oscillations. Now in the software, in order to do this, you can go to the mechanics section where if you click on SR04 echo module distance logger, this will pull up the single channel data logger set to measuring distance SR04. And there's a little gauge here that will show you the oscillations. So you see, this is about 3 centimeters. As I take it far away, it becomes about 10, 15 centimeters, etc. Now, as I let this oscillate, okay, I'm just going to drop the spring. I can plot this data. So the duration is set to 10 seconds. If you make it 0, it becomes a continuous logger, or you can set it to a defined interval. Now in this graph, I can click and drag the y-axis or scroll to zoom it. Okay, now from this graph, what is the period of oscillations? You can go to one peak and say, okay, this is about 4.85 seconds, 4.82. Go to the next peak, this is about 5.8. So the time period is about 1 second. 1 by 1 second is 1 hertz. Another way to find out more accurately the period of oscillations is to use regression, use chi-square minimization for all these raw data points approximated to a sine function, which is a sine omega t plus phi. So that you can do by selecting the region and say sine fit. So now there is a red line that's going on top of these. It's overlaid nicely. And the results are here: 4.82 centimeters of amplitude, frequency is 0.965 hertz. So you could go one step further and try to find out the damping coefficient. So the equation for damping has a sine omega t plus phi into the exponential term, right? E to the power minus. So when you add that in and apply damped sine fit, so now you have the decay constant also here. So that's about 0.045 second inverse. That's extracted from this raw data points. Now, if you want to measure the speed of sound, right? Here we assume speed of sound is 330 meters per second. And using the time taken for this sound pulse to travel from the sensor to the card and back, you can calculate distance by assuming speed of sound. Now, if you fix distance, you can measure the time using the sensor and calculate the speed of sound. Now for that, in the same mechanics section, you have the time trip logger, which measures and tells you the time taken. So it will behave very similarly to the other graph. You have the time graph. But there is also a second derived parameter here where you can put in any equation here where x is the variable that we're measuring. So when I say 33 to x by 2, I'm actually getting the displacement in centimeter units. And that is this distance graph here. So secondary y-axis. If I drag this, I can split it away from the time graph. So you see, I have extracted distance from the time. Okay, but of course you can use it for measuring the speed of sound also. For example, you can use a heated chamber and see how the speed of sound varies with the temperature of air. Now, another sensor that's more useful in some scenarios is the VL53 LIDAR sensor. So this measures distance, okay, but it uses light pulses. So it's got a laser inside and it measures the time taken for the light pulse to bounce from a reflecting surface and come back. So this is more useful when you have, for example, soft surfaces or curved surfaces. For example, a tennis ball oscillating, you can't really track it with the SR04 sound-based sensor because the sound is absorbed by the ball's material, and it's also reflected in all directions because of the curvature. But this sensor works better. Let me select in the software under the mechanics section, distance by LiDAR module. So now it's waiting for the LiDAR module to be connected. Let me just plug that in on the top right corner, matching the SCR SDA pins and the power supply pins. So this is placed here, and it's showing here that it's about 150 millimeters, the distance from this sensor to this card here. Now this is more precise, but it's also slightly slower compared to the echo module. Okay, so similar graph will be achieved with this LiDAR module, and I can sign fit and it'll tell me, okay, frequency is 0.977 hertz. Of course, if you disconnect this, it will go back to, go and find not detected yet, but you can quickly plug it in and start reading things again. Okay. You can, of course, you can save your raw data using the save button here. This will ask you to export this data as a CSV file. And what else? The saving here, you can right click on the graph and there's a bunch of options for exporting as CSV, for exporting as images, SVG, etc. SVG is particularly useful if you're trying to avoid replotting your raw data, because you have your raw points here and you can always change using Inkscape or some other vector graphics tool the font sizes, etc. So that covers your single data logger and two different sensors for measuring displacement as a function of time. Yeah, thank you.